In 1940, Britain prepared for invasion. Conventional anti-tank guns were in short supply. Petrol stocks, by contrast, were abundant and static. Officials sought ways to weaponize surplus fuel. Petroleum Warfare Department. The new department handled petroleum warfare schemes. Trial memoranda described oil as a defensive obstacle. Suggestions included burning ditches and sprayed flame. Previous war papers mentioned older fougasse concepts. A fougasse used buried explosive and loose projectiles. Designers now replaced rocks with liquid fuel. Engineer William Howard Livens brought previous projector experience. His earlier mortar had thrown oil and gas. The principle was cheap tubes and standard bombs. Here, the department inverted the relationship between container and charge. The container itself became the projectile source. A steel drum replaced the traditional excavated cavity. An explosive charge sat behind the filled drum. On firing, pressure ruptured the drum's rear wall. The liquid contents were hurled out as spray. An ignition element turned that spray into burning fuel. The organization named the device a flame fougasse. Planning papers classed it as a mine. It was triggered electrically from a covered point. It was intended for anti-tank and anti-personnel roles. The firing rate was inherently single-shot only. No aiming devices were mounted or required. Coverage depended entirely on sighting and pre-survey. Everything depended on placing the barrel correctly. Everything depended on pressing the switch at timing. The standard container was a 40-gallon drum. Trials used new or reclaimed fuel barrels. Workshop notes mentioned dents, corrosion, and re-rolled seams. Inspectors rejected drums with deep scoring or cracks. A rejected drum went back into general fuel service. Accepted drums were washed, dried, and labelled. Stencil markings recorded mixture type and filling date. Ink entries in depot ledgers tied drums to sites. Each drum represented one prepared defensive position. The fuel mixture varied with supply and experimentation. Early instructions specified petrol and heavier gas oil proportions. The blend was deliberately unsuitable for vehicle engines. Formulations balanced flow, adhesion, and burning duration. A separate mixture, coded 5B, used tar and lime. 5B behaved more like a thick incendiary paste. It stuck to metal and earth surfaces on impact. It burned into place for several sustained minutes. Storekeepers handled 5B drums as controlled incendiary stores. Charges used ammonal cartridges as the propellant explosive. Ammonal was cheap but hygroscopic in damp conditions. To protect it, crews prepared sealed cocoa tin charges. The propellant assembly sat inside a rubberized inner bag. Magnesium alloy turnings were packed with the explosive. Fragments from burning magnesium provided reliable ignition sources. Detonators and primers were taped along the cartridges. The entire unit was wired through a small lid hole. Electric leads were color-coded and insulation-wrapped. The most common pattern was the safety fougasse. This pattern separated the explosive charge until crisis. Construction instructions specified an earthen bank or cutting. Sappers excavated a shallow recess into the side. They left a low platform to carry the barrel. The filled drum lay horizontally, face toward the road. Then only the circular front appeared once backfilled and camouflaged. Behind the drum, workers installed a vertical pipe section. The pipe formed a pocket for the removable charge. The lower pipe end rested just above barrel bottom. A thin cover plate closed the lower pipe opening. The upper pipe end took a simple weather cap. Soil and rubble were piled over drum and pipe. Finished work presented a bare disc and pipe top. From the road, the fougasse remained largely inconspicuous. Vegetation and painted mud completed the visual concealment. Roadside banks and cuttings offered numerous suitable locations. Bridges, bends, and junctions saw particular emphasis in sighting. The propellant charge stayed in store during quiet periods. Magazines held labelled tins in wooden crates with dividers. The charge lists indicated which crate supplied which position. Telephone orders could authorize issuing specified numbers of tins. Only when invasion seemed imminent were charges installed. Teams carried tins, spades, and field wiring gear. They opened the pipe, lowered the charge to position. Dry soil tamped the tin firmly against the drum. Leads ran back to a protected firing point. The firing circuit used a 120-volt power source. Batteries sat in weatherproof boxes behind cover. A simple key or switch closed the circuit on command. Firing parties tested continuity by low-current meters. Test procedures avoided accidental heating of detonator elements. The firing point location depended on tactical field design. Sometimes it lay in a slit trench near crossroads. Sometimes it sat inside a nearby defended building. In all cases, and only authorized personnel held firing responsibility. On firing, the ammonal charge detonated behind the drum. The sudden pressure burst the rear plate inward. Fuel surged forward, following the new rupture path. The jet cleared the drum rim as a sheet. Ignition materials intersected the emerging stream of liquid. The resulting flame spread, formed a short, dense curtain. Reported jets were around 30 yards in length. The effective width approached 10 feet at impact. Duration was brief, typically 1 to 2 seconds. Documentation stressed the jet's shocking instantaneous coverage. Technical notes also stressed the single-use limitation. Once fired, the sight offered only scorched ground. Reloading required new drum, fresh charge, and rewiring. Expectations assumed no time for reloading during action. The device functioned as a prearranged ambush only. Operators were trained to wait for exact vehicle positioning. Diagrams showed preferred impact points on track runs. Instructions emphasized timing just before vehicles reached fougasse centerline. Alternative configurations were developed for particular ground conditions. One was the demi-gasse, using a partially exposed drum. Its propellant sat beneath the horizontal barrel carcass. At ignition, the barrel flipped over, discharging forwards. This allowed use where no bank existed roadside. It simplified digging, but increased handling risks around explosives. Another pattern, the hedge hopper, stood its drum upright. The propellant charge lay slightly offset beneath the base. On firing, the drum bounded forward and upward. Correct hedge hopper placement demanded repeated local trials, and too much explosive threw the drum uncontrolled sideways. Too little lift produced a short, ineffective hop. Reports mentioned drums overshooting intended hedges completely. Others struck the obstacle and broke without projection. War Office guidance eventually discouraged extensive hedge hopper deployment. Commanders preferred the simpler banked safety fougasse layout. The safety pattern offered predictable geometry and better control. It also allowed delayed insertion of hazardous propellant charges. Surviving manuals show standardized drawings and dimensioned sketches. They specify minimum cover thickness over the drum. They set distances from rim to road surface line. They define lead run lengths, back to firing positions. They include notes on avoiding telegraph and power lines. Margins include handwritten amendments from field instructors and officers. Pencil comments record soil behaviors under heavy rain. Annotations mention bank collapses where subsoil was sandy. Others describe difficult digging in chalk and flint layers. Training for local defense units followed a stable pattern. Home Guard platoons attended static demonstrations on prepared ranges. An instructor explained component parts using an empty drum. Students handled inert charges lacking detonators or live explosive. They practiced lowering tins into mock-up pipes carefully. They rehearsed connecting, taping, and camouflaging twin-core firing cables. Only authorized staff attended live firing days with observers. Demonstrations used derelict vehicles or wooden screens as targets. Observers recorded flame spread, smoke density, air and visibility distances. Trial reports noted effective blocking of narrow rural roads. They recorded severe damage to unarmoured and lightly armoured vehicles. They warned that heavy tanks might continue moving briefly. The aim was disruption, obscuration, and crew disorientation. The weapon complemented rather than replaced solid anti-tank obstacles. Checkpoints combined roadblocks, anti-tank obstacles, and fougasse batteries. Maps marked arcs where vehicles would be exposed to flame. Range flags on training grounds translated into imagined hedgerows. Crews learned to visualize flame coverage on actual lanes. Administrative paperwork underpinned every installed battery location. Site plans accompanied by sketch maps went to higher headquarters. Copies stayed with local records and engineer field parks. Each plan identified barrels, of firing points, and route numbers. Recently drawn ordnance survey sheets served as the base. Stamps indicated classification levels and distribution restrictions. Typed covering notes explained purpose and firing authority chain. Signatures from field engineers confirmed completion of installation works. Later annotations recorded site modifications, removals, or upgrades. Procurement files show debates over barrel quality and sources. Fuel companies negotiated replacements for drums diverted to defense. Some correspondents complained about contamination of stored products. Others raised corrosion problems from long-term open-air storage. Engineers argued for thicker drums in vulnerable positions. Treasury representatives questioned additional costs per strengthened unit. Compromises used standard drums with specified inspection intervals. Routine checks looked for bulging ends and leaking seams. Suspect barrels were drained, removed, and replaced from reserve. Storage depots held spare drums, charges, and cables. Each depot kept an index of supplied defensive localities. Truck manifests logged consignments by road junction codes. Local units signed for deliveries using simple receipt forms. Some sites accumulated excess material when plans changed. Redistribution required fresh paperwork and convoy scheduling. The system attempted to align resources with revised defensive lines. As invasion threat receded, redistribution became gradual and selective. Some prepared sites never received full operational charges. The original concept relied on Britain's particular landscape pattern. Minor roads ran between high banks, hedges, and cuttings. Village entries narrowed between walls and elevated gardens. Bridges formed natural choke points over streams and railways. Designers chose these places to concentrate projected flame. A single drum might cover the full carriageway width. In other locations, multiple barrels formed overlapping fields. Batteries of 3 or 4 drums covered wider approaches. Some plans considered 2-tier arrangements on steep slopes. Defense schemes integrated fougasses with road demolition charges. Some bridges were wired both for collapse and flame. If the span remained, flame alone impeded crossing attempts. If demolition occurred, burning fuel complicated any bridging effort. Minefields and anti-tank ditches sat behind flame belts. Planners saw fougasse as one layer in depth. Operational orders described coordinated sequences for firing prepared obstacles. They gave timings relative to enemy approach distances and reports. Units rehearsed simulated triggers based on observation posts and runners. The device imposed constraints on friendly movement patterns. Road control orders listed fougasse roads as restricted zones. Only designated traffic used those routes during high alerts. Clearance signals and code words governed an authorized friendly passage. Risks remained if information failed to reach all drivers. Some local commanders preferred sighting away from main supply axes. Others accepted the risk to gain key road coverage. Occasional complaints appear in correspondence about obstructed civil access. These rarely overrode military sighting requirements in 1940 conditions. From an engineering viewpoint, simplicity reduced manufacturing bottlenecks. Drums were standard items, already in bulk production. Explosive cartridges used existing industrial ammonal supplies. Magnesium turnings came from machine shop waste collections. Wiring and detonators matched other demolition systems already stocked. No precision machining was necessary for core components. Most labour involved earthwork, carrying, and basic assembly tasks. This allowed rapid expansion without specialist manufacturing plant construction. It also eased later dismantling when threats subsided gradually. Reliability depended strongly on discipline in sealing charges. Improperly tied rubber bags admitted moisture over weeks. When that occurred, ammonal lost sensitivity and propellant strength. Manuals emphasized dry storage and prompt replacement after exposure. And inspections opened sample tins to check internal condition. Discolored packing or damp magnesium turnings meant rejection. Rejected charges returned to engineered depots for controlled disposal. Live detonators were removed first under standard safety drills. All steps were logged in unit explosive accounting books. A persistent hazard lay in exposed or damaged wiring. Rodents, tools, and vehicle wheels could sever insulation. Brakes prevented firing or created partial contact points. There was also risk of unintended energizing from stray currents. Guidance discouraged running cables parallel with power lines. Crossings with telephone routes required additional insulation wrapping. Markers on engineer sketch maps showed cable routes underground. On the surface, camouflage concealed but also complicated later tracing. Some maintenance work involved re-excavating sections to inspect joints. Multiple failure modes appeared in trial and maintenance records. One mode involved charge detonation without barrel rupture. Thick or double-plated drums sometimes resisted internal pressure. Fuel vents opened only minimally, giving a weak spray. Another mode involved rupture but unreliable ignition of fuel. This produced spray without full flaming coverage on target. Investigators looked at magnesium quantity and distribution inside tins. They also examined whether liquid composition affected ignition probability. Viscosity changes in cold weather altered atomization and mixing. Sighting errors generated different classes of functional failure. Drums angled too low drove flame into roadside bank. Those angled too high overshot the centre of roadway. Curved approaches altered vehicle positions relative to drawn arcs. Trial boards recommended marking reference stakes during installation. These helped builders keep intended geometric relationships consistent. Later removal of vegetation occasionally changed sightlines unexpectedly. Seasonal growth created new visual cover for incoming vehicles. Engineers recommended periodic review of each site's geometry. Signals discipline affected tactical performance at the moment. Observation posts needed clear authority to order firing. Late decisions risked barrels being overrun unfired by armour. Early firing wasted the single opportunity on advance elements. Some schemes used multiple observation positions with agreed criteria. For example, firing only when second tank reached marker. This institutionalized timing into standing operational instructions locally. Such procedures reduced improvisation and individual uncertainty under pressure. They also reflected the weapon's dependence on precise circumstances. When strategic conditions changed, so did fougasse importance. By 1942, invasion probability decreased as other fronts opened. Improved anti-tank guns arrived in greater quantities for defence. Armoured units trained for mobile counterattack instead of static blocking. Within this context, fixed flame barrels appeared less essential. Some were reimagined as oil mines for infrastructure denial. Buried installations focused on destroying depots and key facilities. Nonetheless, many roadside sites either simply awaited formal decommissioning orders. Removal proceeded according to labour, transport and local priority. Their records indicate most British flame fougasse sites were never fired. Their effects remain largely confined to training demonstrations. Yet paperwork, plans and scattered remains document their scale. Sources speak of around 50,000 barrels prepared overall. Thousands formed batteries across southern England and parts of Scotland. A proportion stayed in reserve within storage areas. Some guarded fuel depots as last resort destruction measures. A few installations abroad later saw actual operational use. Reports from Greece mention flame barriers affecting attacking troops. The design influenced subsequent flame mine developments elsewhere. German and Soviet forces produced related flame mine systems. These used internal gas generators instead of bursting drums. They drove fuel up central pipes to concealed nozzles. And electric or mechanical triggers activated these buried flame devices. Field manuals later described comparable expedients using available containers. Instructions advised combining jerry cans, grenades, and detonating cord. Yet the British model remained distinctive for its barrel-centric pattern. Its emphasis lay on exploiting petrol reserves and typical road embankments. From a handling perspective, the fougasse resembled demolition stores. Units applied similar sign-out and sign-in procedures rigorously. Nominated custodians counted detonators, charges, and filled drums. Counts occurred daily during high readiness periods and alerts. Any discrepancy demanded immediate investigation and written explanation. Central returns summarized stocks across regions for higher headquarters. These appeared as tables listing districts, sites, and totals. Columns differentiated between installed, reserve, and defective equipment. Supervisory officers certified returns with signatures and unit stamps. Transport logistics created additional complications for coastal counties. Narrow roads already handled troop, supply, and refugee movements. Moving drums and charges added weight and congestion to columns. Vehicles carrying fougasse materials needed careful packing and restraint. Spilled fuel from damaged drums posed fire and slip hazards. Orders insisted on wedge blocks and rope lashings inside lorries. Drivers received instructions on avoiding sudden braking on wet gradients. Any collision risked rupturing both ordinary and fougasse stores. Convoy commanders logged route incidents and near misses in diaries. Maintenance regimes extended across the network of prepared sites. Engineer sections followed circuits visiting each battery sequentially. They inspected exposed pipe tops, drum faces, and camouflage. Rust streaks or bulging paint indicated internal deterioration processes. Soil settlement exposed outlines that compromised visual concealment effectiveness. Vegetation sometimes grew across the drum face and pipe. Crews cut carefully, avoiding recognizable human trimming patterns. They distributed clippings irregularly to mimic natural plant shedding. Footprints around the site were brushed out before departure. The fougasse's short duration imposed specific tactical interpretations. It could not form a continuous barrier like flowing ditches. Instead, it was categorized as a sudden interruption device. Smoke and flame offered concealment for accompanying small arms fire, and burning fuel could cling to soft-skinned vehicles and tyres. Even when armour withstood heat, periscopes and vision ports fouled. Road surfaces became slick, uneven, and scattered with burning patches. Follow-on vehicles faced both physical and visual disruption simultaneously. Planners counted on disorder to create time for other measures. Within after-action planning games, staff officers modelled possible engagements. Sand table exercises placed markers representing drums along chalk roads. Toy tanks drove routes while instructors paused for decisions. At predetermined markers, coloured wool indicated projected flame envelopes. Participants assessed which routes remained open after successive firings. They adjusted minefields and obstacles in light of these assessments. These exercises helped embed fougasse use into local defensive doctrine. They also clarified where installation effort produced minimal marginal benefit. Less critical routes were then removed from construction schedules. Removals followed procedures mirroring installation but in reverse. Teams first disconnected firing leads from battery terminals safely. They then opened access pipes and extracted remaining charges. Recovered tins went under escort back to explosive depots. Detonators were removed and destroyed according to standing orders. Drums were drained if still filled with fuel mixture. Liquids were either reclaimed or burnt off under supervision. Empty drums were crushed, cut or repurposed for non-military use. Final site inspections confirmed no visible hazardous remnants remained. Despite decommissioning, some barrels escaped full recovery efforts. Later decades revealed corroded drums in former defensive positions. Archaeological surveys occasionally uncovered earthen banks with remains. Finds typically included rusted hoops, plug fragments, and oily soil. Specialist teams handled any lingering fuel contamination or explosive risk. Recovered items sometimes went to local museums and archives. Documentation and relics together reconstruct the wider operational pattern. They illustrate a dispersed, latent system of controlled flame. That system depended on basic containers, modest charges, and planning. The flame fougasse also persisted in technical manuals abroad. Post-war documents from other armies described similar expedients. They repeated core components of container, rupture, and ignition. They stressed exploitation of readily available fuel and metal stock. They treated such devices as interim expedients, not primary systems. Yet the original British development reflected specific 1940 pressures. It addressed weapon shortages, petrol surpluses, and expected road fighting. It formalised an improvised concept into a nationwide network. Its effectiveness rested less on complexity than on disciplined preparation. The mine that threw fire remained mostly unused in combat. Its existence nonetheless shaped defensive planning and resource allocation. It showed how industrial byproducts could be adapted systematically. It turned everyday containers into one-shot flame projectors on roadsides. It required surveyed sites, trained operators, and strict documentation. It translated fuel, explosive, and earthwork into controlled directional flame. It remained dependent on timing, distance, and line-of-sight assessments. It represented a defensive doctrine built around holding the next hedge. Its record now survives mainly in files, diagrams, and scattered relics.